square is acceleration. So g times r is this piece, little m cancels out c square at the bottom. These numbers we just plug in. This are 980 whatever centimeters per second square. R is the radius of the earth, c is the velocity of the light. All these are well known in plug it in. You will get a number 10 to the minus 9. So that is how small this ratio is in some absolute terms. That is how small this force of gravity is. If you were on some huge, very hot, heavy object, say even the sun, then big M will be bigger, and so this ratio will become bigger. If you go very near a pulsar, big M will still be about the size of a mass of a star, but little r will be 10 kilometers. So once again, this will be big. So except in those situations where this number has some chance of becoming closer to 1, on the Earth certainly this is very small. So you plug in these things, you get that 10 to the minus 9. As I said, move the mass to the mass. Object cancels out. So to produce enough gravity to bring out general relativistic effects requires really astronomical or cosmological objects, black holes, early universe, pulsars maybe, how important it is. Unless you are beginning to study phenomena of that scale, you don't really need general relativity to explain all other science. So, in fact, for a long time after Einstein constructed general relativity, the sole experimentally measurable consequences were extremely erudite things, very delicate, very minuscule effects. The bending of light as the light goes by the sun was Einstein's relativity, general relativity predicted that the light will be attracted by the sun's gravity and will bend. You could observe that in an eclipse, and that's what was done. And minute discrepancies in the orbit of the Mercury Newton for very fine effects. That's all that was available. Few more things are available now, but even now, unless you do studies of things near black holes and so on, or have theories of early universe, still theories, you don't really get to experimentally see general relativistic effects. So it's even more remote from day-to-day life or even ordinary science, including atomic science, nuclear science, whatever. But of course, people were sure, especially right-thinking people were sure that this was true because it was so beautiful. Hung together so well, had to be true and sure enough. Little by little, it was verified, the bending of light and the orbit of Mercury and so on.
Sorry, just one comment. Even though it's tiny, apparently GPS they do take general relativistic effects.
Exactly.
Otherwise, in 3-4 days, it will go off by.
So if you want to go to that level of accuracy, GPS does now require that effect. But technologically handicapped people have never used GPS. I don't know whether General Post Office or what it is. Thanks. No, point's right. So already we are there now. What you're saying is that to be used even today. Already today. So let me move to quantum theory. And I have not done really anything other than two packages I have shown where they are done. The relativity packages. One is at high speed, the other is at high gravity or high acceleration. And how both of them are in fact not easily available in terrestrial quantum. Quantum theory. Now this really was demanded by experiment. Quantum theory was invented because funny things were going on. You observe them and there's no way to understand it. Spectral lines, why are there spectral lines? Why aren't atoms collapsing? Etc. It's a whole bunch of questions. These are things you studied in your courses as motivations behind quantum theory. So all these things were classically, these were behaviors of atoms and molecules. Again, quantum mechanics was not felt necessary in day-to-day life, in macroscopic phenomena, and that is why you didn't need anything other than classical physics until we began to do experiments at the atomic and later subatomic level. Till then it was not visible, it was not observable. So when you looked at the behavior of atoms, molecules, spectra, chemical behavior, you realize that classical theories are not working there. So quantum theory was invented for them. And like relativity, quantum theory was a profoundly revolutionary effect, demanded a complete change of philosophy, aptitude to think differently, indeterminism, uncertainty, discrete values of energy, angular momentum 1 times h bar, half times h bar, 3 times h bar, can't change continuously. Energies can be of certain values in the atom, in the molecule, anywhere. The phenomenon of tunneling, when you have a barrier which classically you shouldn't be able to climb over, quantum mechanically there's a chance you will appear on the other side. So, all these are new results. Once again, I'm not deriving all of them. I'm assuming you've heard of these things. I'm just listing them. What is the domain where quantum theory is a must? Well, in terrestrial phenomena, cars and so on, it's not a must. You can live without it. It becomes important when you go to small things. So atoms, molecules, that is the domain for which it is invented. Of course, quantum theory is supposed to hold, like relativity is supposed to hold all the time for any system. Quantum theory also holds for any system, including you and me. Big things, cars and so on. But the quantum mechanical uncertainties in a car, you can measure the car's speed and position pretty accurately. And that's because your levels of accuracy are so small, you won't know that there's a little uncertainty. So large objects, the various uncertainties incoherently cancel, so you don't really see them in macroscopic objects. You had to go to microscopic objects. By microscopic, I mean sub-microscopic, atomic, molecular. But people have already seen them. So in fact, the unknown phenomena, strange phenomena were already observed, and the theory was designed to take care of them. So it is only when you consider small systems at the atomic and smaller still levels that quantum phenomena become significant. Larger, coarser macroscopic objects, these fine effects get washed out. So these are the domains. Quantum theory and relativity. Do they overlap? Because if they overlap, and where they overlap, you have to use both. And when you have to use both, you have to make sure that the principles of one don't clash with the principles of the other. So let's look at the atomic and molecular phenomena. That's what quantum theory was invented for, where quantum mechanics really is needed and gives substantial results. Do these systems require relativity? So let's look at special relativity. First, what is the criterion? The objects involved should be moving speeds comparable to the speed of light. What are the objects? Well, typically when we say we study atoms and molecules, we study the electrons in those atoms and molecules. And the electrons are, in the quantum sense, going round and round and moving at some speed. How much is that speed? Typical speed of, you can calculate in the hydrogen atom, in the normal hydrogen atom classes, the typical kinetic energy of the lowest orbit, let's say, of the hydrogen atom. And you can calculate from that average kinetic energy the average velocity. And V over C turns out to be this famous fine structure constant. This is there in every quantum mechanics on the hydrogen atom chapter. It's E square over h bar c, which is 1 over 137 approximately. So there, now we're getting there. V over c is not 1 in a million or something, it's already 1 in 100. But of course, the relativistic effects are the square of that, so it's 1 in 10,000. So it's 0.01%. But of course, very soon, even at that time, and certainly now, spectroscopic properties are measured to far higher accuracies than that. And you want to make calculations to that level of accuracy, you have to introduce relativity. And many other things. But, so at the atomic level, if you are willing to live with less error than, say, typically 0.01%, once again, you can neglect special relativity. So in the early days, when the idea was not to build precision instruments and so on at that time, was to make sure you understood the phenomena, spectroscopy, splitting of lines and so forth, most of them could be understood without going into relativity. So it's not that the creators of quantum mechanics didn't know relativity, in fact some of them were the same guys, the Einstein. So it's not that they didn't know whatever the fact there's no great urgency to marry relativity and quantum mechanics, making your life unnecessarily difficult. Quantum mechanics is hard enough. So they work with non-relativistic quantum mechanics. They've got beautiful results. So unless you want to go to very high accuracy or study some very delicate effects of the order of 1 in 10,000, you don't need relativity. The need for general relativity is even more minimal. The gravitational force between the electron and the proton is even more negligible. So it simply plays no role at all in atomic and molecular physics. electrical forces are much stronger. It's the electrical forces that govern atomic and molecular physics and chemistry. So, wisely, quantum theory was invented in non-relativistic context. That's what you study in your basic quantum course, non-relativistic quantum mechanics, non-relativistic Schrödinger's equation. And that is a sensible thing to do. And consistency with special relativity was not of immediate concern, let alone general relativity. But as ordinary quantum mechanics, non-relativistic quantum mechanics settled down, it was clear, it was correct, it was explaining many things. The more powerful theorists said, all right, let's see if we can combine with relativity. Even though the experimental motivation was at the level of 0.01%, conceptually it is very important, both principles are true. So the effort started a little later. So we start with special relativity. It's clearly easier with the relativity. It's also more likely to be of at least 0.01% effect in atoms. The general relativity effects will be much more than that. So introduction of trying to combine relativity special with quantum mechanics was done not because of experimental compulsions at that time. Because already by 1928, these guys who can't be kept back, Dirac, Fermi had started introducing already a way of doing these things. But because of a desire for theoretical completeness, for relativity, for quantum mechanics, both are true. Surely there should be a single formulation where all the principles apply. So the first step in this process was the invention of what is called relativistic wave equations. We're slowly going to get into a few equations, I'm afraid. That's why I said quantum mechanics is necessary as a background for this class. So, yeah. Now, relativistic wave equations. Remember that write down the non-relativistic Schrödinger's equation which you see. And this equation is clearly not relativistic. In the sense you can apply Lorentz transformations on it and find that t goes to t prime, x goes to x prime, the equation will be invariant. But also the fact that its first order time derivative and second order space derivative means it's not relativistically invariant anyway. Space and time are on equal footing. Special relativity. So you can check this is not a relativistic invariant equation. Of course, we all knew that it's meant for the non-relativistic context. And how one derives this equation is a long story, I can't go into it now. But loosely speaking, people will tell you that it comes from resemblance with the ordinary classical equation for energy. The right hand side should be the Hamiltonian. Hamiltonian is energy. Energy is p square over 2m plus potential energy. And P, by de Broglie's hypothesis, is h grad, and B is V. And so the right hand side is p square over 2m. And that is how you construct the Schrödinger's equation. That's not proof. And that this will work is something comes from deep intuition of understanding of quantum mechanics, of classical mechanics also. But whatever here is the equation. It works. And it comes from that analogy. And it's not relativistic for the same reason that this equation for the energy is a non-relativistic equation. This is half mv squared plus potential energy. This is not a relativistic equation. So you want to have a relativistic wave equation instead of this. You start with a relativistic particle formula where the energy square is p square c square plus m square c4 plus potential energy plus potential energy. Maybe it has to be square. So the last term can be added in a lot of ways. You can add it inside and square in various ways. For a free particle, that V is not there. So here's a particular situation. Now you convert this into a differential equation the same way the Schrödinger's equation was. Wherever you see E, you put d by dt. Wherever you see t, you put d by dx, and you get this equation. Just like the way Schrödinger's equation was, except this equation now is relativistically invariant. You make Lorentz transformations out to a new frame. There is a new x called x prime. There is a new time called t prime. You plug in derivatives d by d prime square and d by dx square. You will find this equation does not change. This is a relativistically invariant equation. It's called the Klein-Gordon equation. Which are two Klein and Gordon. But
this equation cannot be correct because it's V, V.
No, that depends on what V is. It's just a particular equation. That's an unsolved. Many people do these things. They add V into the energy square, they will add V outside.
This is not potential energy.
No, this is just an object. That's why even earlier I said the V, it just stands for the potential effects. It could be. It's not standard potential energy, which has no meaning anyway. So it's just a way of saying there can be other terms. What he's saying is that there are people who use P plus V whole square times L square C square, various things, scalar potential, vector potential. So I don't want to go into those things. It's just a symbol of the fact that an interacting wave equation can have other terms, which stands for the forces. It's just one example of that kind. And the free Klein-Gordon equation doesn't even have that. And this is not the most complicated thing you can write. You can write more complicated. Now this equation unfortunately could not be used by them because if you try to use this in the place of ordinary Schrodinger's equation, you say, well, it's relativistic, that's nice. But in ordinary Schrodinger's equation, you do all kinds of things with the wave function. The most fundamental thing is you square psi and you get psi mod square. That's supposed to tell you the probability of finding the particle. Here, psi mod square is not even conserved in time. If you take this equation and see how psi varies with time, and then calculate how psi mod square varies with time, psi mod square changes. So the probability, if we normalize it to 1 at the beginning, at some time later on, the probability will change of its being somewhere away from 1. That clearly makes no sense. So there is something else which is time invariant, that is psi star dt psi. You can show that this is time independent, but this is not always positive. Sometimes it's positive, sometimes it's negative. Therefore, it's not a candidate for probability, which cannot be negative. So there was problems in using this equation. Another equation was invented where I'm going to skip over very fast because it's complicated in ways that are not important for us. It's the so-called Dirac equation. And there, instead of having second order derivatives, you had a first order there. These alphas and betas are matrices. This is so constructed that given some properties of alphas and betas, this equation will be Lorentz invariant. And it's an equation where psi square b3x can be thought of as the probability because it is conservative. It also has all kinds of bonuses. It has 4 components, therefore it has built-in spin in it. I'm not going to spend much time on it because you have to know sort of the algebra of the alphas and betas and so on. It's not related to our particular story, for which the Klein-Gordon equation is a good enough example. But here's another example which became very, very useful. It had its own problems, even though probability was positive and conserved. It had particles with negative energy, and you had to do all this double talk, which I did successfully. There are, of course, no negative energy particles. That makes no sense. So we said the negative energy particles can be thought of as all filled. This is copied from solids, where you think of all the energy levels as filled, and you think of poles being created. And he said the real world is also like that. I don't want to dwell on that story because I don't want to particularly protect or defend that story. It turns out we don't need all that stuff. But for a while, it was used and it gave an indicator. They were deep intuition, they were right, except there are no negative energy particles, there is no such thing. This equation here. I don't want to discuss this too much other than for the record mention it. That here is one more equation which has its own set of problems. But the problems that are there are actually much deeper than the problems of either this equation or the other one, which I can try to get something here. Say, or this equation. They're all equations, they have some problems, but the real problem is something much deeper, and we can see that by the following argument. No relativistic equation will do. Whether it's Klein-Gordon or Dirac or any other complicated thing you might have with the V here, doesn't matter. As long as you have a differential equation, it really cannot be a valid equation for real physics of relativistic systems. Why is that? We know relativizing quantum mechanics therefore is not just a matter of finding a relativistically invariant equation. It is bound to be inadequate because remember, as the formula E equal to m square indicates to us, matter and energy can be interconverted. And experimentally that is true. The real world, as we know now, matter and energy are constantly being interconverted. particles combine, disappear, annihilate, pairs are created,